in maintaining, developing, and offering for free such an amazing tool. And not only that, but Uri has also been an exemplar teacher, and he has developed what I believe is an extraordinary course for students from all across the university. And again, I think this is part of his commitment to the complex systems community, that even though the course is offered as part of computer science, he actually gives preference to students from other departments and other programs, so they can be exposed to computational research and agent-based modeling. You know, I could go on and on and on about all the things. He has served NICO also extraordinarily well by being in our executive committee several times, being part of our advisory board, and being always willing to take the time and the thinking and the care to contribute to the community as a whole. So it really gives me, as I said, an enormous pleasure to award this plaque to Uri and to recognize his contributions.
Thank you. Congratulations.
Thank you very much.
Congratulations. And with that, I have the immense pleasure to introduce today's speaker, joining us from the University of Michigan, Daniel Romero, who's an associate professor there in the School of Information Science with a courtesy appointment in computer science. He does not need a lot of introduction. He's a brand name in everything social media, everything internet. And among all the wonderful things that he did, I'm sure many of you know about it, I want to point out one thing that makes it quite special that he's here today. So he did a postdoc at NICO back in 2012, 2014. And during that time, he was working with Brian Uzi, a person through whom I got to know him. And since then, we have collaborated. So it's another invitation for you to look around in this room, because you will find your future collaborators here. So with that, and without further ado, let us welcome Daniel.
Thanks, Agnes, for the super generous introduction. I'm really excited to be here. As Agnes mentioned, I was a postdoc here 10 years ago, so I have strong connections to NICO, and now my student helping is starting a postdoc at NICO 10 years later, so it's like the institute that keeps on giving. So really, really excited to be here. Yeah, I'm going to talk about networks, identity, and linguistic innovation. If I have time at the end, I also want to talk about other work that we're doing in our group, but sort of depends on how I do with time. Throughout the talk, if there are questions, please feel free to raise your hand. I can adjust the time as necessary. I like to have as much discussion as possible. Most of what I'm going to be talking about is a work in progress, so your feedback and your questions are definitely very, very helpful. So this is joint work with my colleague, David Jurgens, and our PhD student, Aparna Ananthasubramaniam. And basically, the question of understanding what is responsible for the diffusion of linguistic innovation, looking at it from the social media angle. And to kind of, sure this clicker works. I can just click. Actually, no, it's just not advancing at all. Okay, now it works. All right, cool. To motivate the problem, I'm going to show you a few fun examples that try to make the point that linguistic variants are often adopted regionally. And it's not anything that's going to surprise anyone, but it's still kind of fun to look at this example. So here is, the colors look really strange, but I hope that's not a problem for going forward. But anyways, here's a map of the US that shows where people use the word highway versus freeway. And so you can see there are clear geographic correlations there. Here's where people use the word tennis shoes versus sneakers. Here is where people use to refer to a soft drink, pop, soda, or Coke to refer to any type of soft drink. Here is Oh, sorry, I'm just distracted by all the things popping up. That's all right. Here's where people use the word coleslaw, which is what I say. In other places say slaw. When referring to a group of people, sometimes people would say you guys, sometimes they'll say you all, and apparently sometimes they say you all without blending the two words together, which is kind of fun. And so clearly there are these geographic correlations. And the point of the study is try to understand what are the sort of drivers of these geographic correlations. And we're going to be looking at two main drivers that have been studied in the social linguistics literature. The first one is this idea of performance of identity. And so here the idea is that when I choose the words that I use, I'm going to be thinking about my own identity, maybe my demographic identity, as well as the identity of people who are next to me, who are going to hear me say this word. And then I'm also going to consider the type of identity that the word itself signals. And if the word signals an identity that's consistent with my identity and the identity of others, then I'm going to be more likely to use it. And because people around me tend to have similar identity as mine, then we're all gonna kind of use the same words, and that's what kind of explains these sort of correlations, right? That's kind of on the one hand. On the other hand, there is network homophily, which we're kind of all very familiar with, right? This idea that, well, the words that I use are determined by what kinds of words I get exposed to. And because of network homophily, people who are my network connections are also close to me geographically, and so I'm going to end up using the same words that they use, and that's what explains these geographic correlations, right? And of course, there can be like a entanglement between these two effects, right? Because network homophily exists in other dimensions besides geography. It also exists in terms of demographic identity, right? And so the goal is to try and disentangle these two and ask the question of whether we actually need to incorporate both of these things into a model in order to kind of capture this diffusion dynamics. And the kind of main hypothesis that we have is that you actually need both of these factors, that you actually need to model both the structure of the network as well as the identity of the nodes in order to kind of do the best possible job at capturing these spatial properties. So that would be the kind of main hypothesis I'm going to try to kind of show you, that we kind of have some evidence for. And then we're also going to get into why it is that you need both in the sense that we're going to try to ask the question of when is one sort of driver more important than the other. And to explain this, we're going to be thinking about different types of geographic locations, in particular urban and rural counties. And the story here is going to be that for transmission between urban counties, this is going to be driven maybe by weak type diffusion, the type of diffusion where you have people who have weak network connections and that have very different identities, and and the words kind of diffuse in this way, the sort of Granovetter strength of weak ties arguments. On the other hand, the diffusion across rural counties is going to be largely determined by identities. So this would be the kind of strong tie diffusion where pairs of people have very strong network connections and also share a lot of their identity. And the kind of sharing of identity is going to be crucial for the transmission of the new words. And I'll talk a little bit more about, how, like the theory behind this and how it works. But this is that's the main hypothesis we wanna answer and or we wanna test. And of course, there are some challenges that come with this, right? So the first challenge is that it is difficult to answer these questions empirically, so only using empirical data, in particular because while we can observe, if we're lucky, instances of people that chose to use a certain word versus another, and when they used it, it's harder to get at why they did so. Was it because the exposure? Was it because of the identity? It's much more difficult to get at that just from empirical data. So it's kind of hard to disentangle kind of network structure from the identity empirically. The other challenge is that if we want to track these cascades of diffusion properly, we want to track them from like the very beginning to the very end, or at least for a long time. And importantly, we want to track them from the very beginning. So we're going to have to do some work in order to get data that looks like that. Okay, so now let me tell you about how we're going to approach the problem. So what we're going to do is, for the problem of the data, how do we get these cascades? We're going to systematically identify new words that appear on Twitter, and we're going to track their diffusion. And then what we're going to do is we're going to develop an agent-based model that is going to simulate the spread of these words. And through this model, we're going to be able to compare the actual cascades of diffusion with 4 different simulated counterfactuals, where we can, because we control the model, we can actually disentangle the different effects. So we have a model that has both the identity and the network drivers. We have a model that has only the network driver, another one that has only the identity driver, and then a null model that has neither one of the two. And so we can compare which of these kind of work better. So let me give you some of the details about the model. I'm not gonna kind of give you like the equations or anything like that. I'm just gonna give you a kind of high-level assumptions that we make. So the first assumption is that we have a network that's fixed, given to us somehow. We're also going to assume we have some data about the identity of the agents in the network. This is demographic identity, and I'll tell you about that in a little bit, but that's sort of given to the model to begin with. And then what's going to happen is we're going to have a set of initial adapters that coin the word. And then based on the identity of those initial adapters, the identity of the word itself is going to be determined. So those initial adapters kind of register the identity of the word itself. Then imagine that some agent gets exposed to a new word, and now it's going to decide whether it wants to use it or not. And when it decides based on what we call this mental representation that the agent has about the word. And this is where kind of all the interesting assumptions come in, right? So there are 4 different types of assumptions. The first one is the stickiness of the word. And this is basically asking how, this is the thing that's inherent to the word, and it asks how salient is this word. And so this might be due to the fact that maybe this word is about a topic that is really popular right now. Or maybe it's a word that is that works for various contexts, and so it's a very useful word to use all the time, so people use it all the time. Or maybe there's some linguistic property of the word that makes it catchy and people like to use it. It's fun to type it, or it's fun to say it for some reason. So it's all about kind of the word itself. Then there is novelty and familiarity. And this is about the frequency and recency of exposure to the word by the agent. And here, on the one hand, we have that familiarity is good. So if the agent hears it a lot, then it's going to be familiar with the word and more likely to say it. But the agent is also going to value novelty. And so if it hasn't heard it in a long time, that kind of gives it a little boost. And so these things kind of go something a little bit against each other, but we incorporate both into the model. The next one is relevance. So this is a similarity. This is where some of the identity issues come in. So this would be the similarity between the agent's own identity and then the identity that the word signals. That again was determined by the initial adopters. And so the more the similarity, the more likely the agent is going to use it. And finally, we have variety and relatability. And this is basically asking what fraction of the neighbors of the agent have used the word, the more the better. And this is going to be weighted by the weight of these edges. This is a weighted network, so how strong of a tie they have, but also the similarity between and the identity between the agent and the neighbors, right? And so this is where, again, the identity component comes in as well. So as you can see there, and so if the agent decides to use the word, then the neighbors will get exposed, and then they themselves will sort of change their mental representation of the word, and then decide whether they want to use it or not. Yes?
So essentially, you are going to define a probability to use the word that is dependent on those variables.
Yeah.
And is that function going to be linear on the variables or non-linear? And is it, do you do some kind of normalization for the values of each one of the variables?
It's very nonlinear. So, and again, like the full details of the functional forms of these are hidden, but like it's nonlinear. So, for example, the novelty factor makes the recency effect kind of decay exponentially. So there are a lot of like nonlinear factors there. Then your second question was there a type of normalization?
Yeah, I mean, there's stickiness between 0 and 1.
Yeah, it's some value between 0 and 1, so they get normalized, and at the end we have some probability. Yeah, yeah, and I mean I could point you to a paper.
No, it's just those general.
Yeah. That's definitely you have the right idea. Yeah, for sure. Yeah.
So you showed us those maps in the beginning with you all and y'all and stuff like that. So there was definitely clearly a geographic effect there.
Right.
Now here, geography isn't represented explicitly. It's just in the strength of the tie. Is that right?
Yeah. No, the geography will be explicitly. So this is kind of like how the agent-based model works for any network. But when we actually run the experiments, the agents themselves are going to be geographically located somewhere in the map. And so geography will be very explicitly sort of modeled in the simulations.
But then how does that affect these probabilities?
It affects probabilities in the sense that, for example, when I talk about identity, location is going to be one factor, one dimension of your identity. And it also affects it in the sense that when we compare the quality of the simulations, we're going to do so by checking whether or not the correlation, the geographic correlation we see in the actual data is also present in the simulations that the model outputs. Yeah. Great. Cool. So, all right. So as you can see, the identity factors are kind of like sprinkled in different parts of the model. But you can imagine how if I wanted to rewrite the model such that it doesn't involve anything about identity, I could just sort of remove some of these assumptions. So the word doesn't have any identity, relevance is no longer a thing. I don't weight the kind of edges by the similarity of identity. I can easily kind of change the model to turn on and off the identity components, right? And so that's exactly what we're going to do. We're going to have four different models, the full model, as I described it. And we're going to have this network-only model where, as I said, we're going to remove all of the identity stuff. And so the mental representation here will only depend on the frequency, the recency, and the number of exposures. Then we're going to have an identity-only model. Now here it's a bit trickier because I cannot just sort of forget that I have a network because the nodes have to be exposed in some way. So what we're going to do is we're going to reshuffle the edges of the network such that we eliminate all of the homophily that may be there to begin with. But we're going to maintain the degree distribution. In fact, we're going to maintain the degree of every single node in the network constant, even in the identity-only model. And then finally, we're going to have a model that is what we think of as a null model, where we have no network and no identity. So we remove all of the identity parameters, and we also reshuffle the edges. But importantly, we're going to leave constant the population size, the degree distribution, the actual degree of every node stays the same, and everything else about the model. And so, for example, if all of the kind of geographic correlations we see are just based on where are the most popular places in the US and where the popular people live, and nothing about network homophily or identity, then this model should capture that, should capture some of those trends, right? Okay. Now, let me tell you about the actual, how we actually set the models of the parameter. And what we do is, most of them are going to come from these 10% Twitter data sample that we get at the University of Michigan directly from Twitter. We got 10% stream coming in all the time. This goes from 2012 through 2020 for this particular study. And so we're going to use that data as much as we can. And so what's going to determine who the agents are is going to be who's on Twitter during that time period, who's active, and also who has geolocation turned on where I can see where those users are. And this is a very small fraction of all of the users that are on Twitter, but in total it's a large number of users. We have 4 million of them. And now we have the agents actually placed in a location somewhere. Then for the demographic factors, we're going to track 5 different ones: the location, the census tract where they live, or where they tweet from, race and ethnicity, socioeconomic status, languages spoken, and political affiliation. Now, here's where we have a bit of a limitation because we don't actually have very super clean data that can tell us all of these details about each person on Twitter. For some of these, there are algorithms we could use to try to infer that. So for example, for political affiliation, there are some things out there maybe for race, but we don't use such algorithms for 2 reasons. One, they're not reliable enough. And 2, there are some ethical issues with using them as well, which I'm happy to talk about, but I won't get into now. Point is, we don't use them. What we do is we're going to do basically what amounts to some smoothing, where we're going to assume that every agent's demographic factors are going to be based on the composition of the demographic factors in the census tract where they live. And so it's this sort of smoothing assumption that we think is fine, given that we're going to look at the kind of diffusion dynamics in a much larger area than the census tract, like in the whole country. But it is certainly a limitation. Okay, and then for the edges of the network, they're going to be based on mutual mentions of users on Twitter, so who mentions whom, both in kind of both directions, and the edges are going to be weighted by the number of mentions. And then there's one parameter that actually that is a bit harder to tune or sorry to determine without actually looking at the cascades, and that is the stickiness parameter. How hot is this word? And so what we do for this one is we're going to basically match it to be the optimal parameter that will sort of give us this, as close as possible of the adoption of the word in the real data versus the model. So we're going to do some grid search and tune this parameter to be the best they can be for each one of the words. Okay, so that's the parameters, and now I'm going to tell you about the actual words that we track, right? So we'd like to have words that are linguistic innovation, so words that are brand new. We don't want to have things like words that meant one thing, but now they start to mean something else. We want to have actual brand new words. And so to do that, what we rely on is urbandictionary.com, which is, you might be familiar with it, is this crowdsourced dictionary for slang. So this is the place where you find all of the kind of latest ways that people talk, and particularly in social media, the words they use. So we started with like over 1 million tokens. But then we start with that and we have to start to filter out a bunch of things that just doesn't work for us. So the first thing is we remove anything that is in the actual dictionary. Things like goat, that again may mean something else, I don't know, but it's a pretty standard word, so it's not a linguistic innovation. We removed all named identities, or named entities like iPhone, so we have some data to do that. We removed things that didn't take off enough for us to be able to measure any type of meaningful geographic correlation, so things that were not used more than 1,000 times get removed. We remove words that were innovated too close to the beginning of our study, so before 2013. We remove basically things that are duplicates of each other. So a small variants of two different words that people use to really mean the same thing, and we check that they have very similar geographic correlations, and so we kind of combine them and we remove the duplicates. And then we manually filter the rest of the words and still find that we need to remove some stuff. So things that are mostly used because of misspellings, like avocado, or things that are actual dictionary words that get put together, like bath salts and things like that. And at the end, we end with our, coming from 1 million to 76 words that remain that are actual, like manually validated. Here are some examples of them. Linguistic innovations that people use in interesting ways. All right. So those will be our kind of empirical data. All right, so a little bit more about the setup of the model. So for each of the words, what we're going to do is we're going to find the first 10 adopters of the model. And again, the identity of the word is going to be determined on the identity of those users. And then these are going to be assigned as the kind of seeds for the model to run the first adopters, right? We're going to tune that stickiness parameter by doing some grid search and try to match the actual usage of the word to the best we can, and set that parameter to be what it needs to be for each of the words. And then with those parameters that are set, we're going to run 5 trials of the word using the model. And then we're going to start comparing the simulated cascades with the actual empirical ones. And so here is how we're going to test whether there is agreement. And we're going to do so in 2 different ways. The first way is we're basically going to compare the correlation, the correlation between the completely finished cascade, simulated one, versus the completely finished cascade, the actual one, the empirical one. And we're going to ignore sort of how things got there. We're going to ignore time for this first initial test. And for that, we're going to use what people typically use for this kind of like geographic distribution correlation, which is this least L measure, which is basically this measure that is used for spatial correlation because it considers both the correlation as well as the autocorrelation. And so that's kind of what people have used for this type of comparison in the kind of geospatial literature. And people have done work to see, what range of least L constitutes, high similarity, medium similarity, low similarity. So we're going to follow that. And basically anything that's greater than 0.4 is considered to be very similar. Anything that's larger than 0.13 is considered to be broadly similar. And anything below 0.13 is not similar. And so here are some examples. I know it's a little bit hard to see and they're small, but here's one. So on the left here is the empirical data, and on the right is the model, the full model. And this is an example that has an L of 0.47. So this would be in the very similar range. And so it's not perfect, it's not like 1. And you can see that the word actually spread part of Texas, a little bit kind of south, and then up here the coast. And the model got like part of the south and some of the coast, but it didn't get enough of Texas and not enough of Louisiana here, so it missed a little bit. But there's quite a bit of overlap between the two. If we look at one that is in the range of broadly similar, then it's this one. Again, this is where it's spread on Twitter, and then Twitter missed, the model missed a large area here where the word actually spread, but the model didn't capture it. And then if we go to the not similar at all range, this would be an L of 0.07. Here we have the word actually spread mostly in Mississippi, in this area over here. And for some reason, the model just was spreading in Louisiana and Texas. And so the overlap is very small. So just to kind of give you a sense for what this looked like. Okay, so we're going to then compare the performance using this measure of the 4 different models against the empirical data, right? And so here's a word. We're going to use the same initial adopters. We're going to run the model using the full model, and we'll get some result. In this case, we get an L of 0.46. We do the same thing, but now using the identity-only model, we get some L. We do the same thing now using the network-only model, we get some L. And in this case, we see that the full model gives us, for this particular word, higher L than the other 2. And then we do the same thing for the null model, and the null model performs really badly for this word. And that will be the sort of exercise that we're going to do. That's the first measure of performance. We're going to use a second one where we're now going to actually start to pay attention to time. And in particular, we're going to start to pay attention to, can we identify pathways of transmission? So pairs of counties where we observe that when the word shows up in one county at some time, then later it shows up in the other county. And can we identify those important transmission lines in the simulated work, right? The simulated cascades, right? And of course we can, because we have the timestamps from the actual data, we have the timestamps from the model since we control the model, we can identify those pathways in all of our models and then in the empirical data, and so we can compare the pathways, right? So let me just give you some details about how that works. So we're going to say that if we have 2 counties, say I and J, the pathway strength between those 2 counties is going to be the time series correlation between the word usage in county I at time t and the usage of that word in county J at a later time t plus 1. And for that, we use these adjusted handles tau that is adjusted for 0 inflated data, because for our data, most of the counties, most of the time have no usage of the words. So we need to account for that. And it's basically going to be high if the 2 counties are synced in the way that I described. And then we're going to basically see if there's a match between the empirical pathway strengths and then the simulated ones by basically measuring the likelihood of an empirical pathway given the simulated pathways. And so to give you a sense, here is, I'm showing you a map here where I'm highlighting the pathways, the pairs of counties that have the strongest pathways, the strongest measures in this measure for the full model. And so you can see that, there are kind of things that you would expect. There are sort of lots of connections across cities, connections kind of going from coast to coast, which is what you would expect, as well as some kind of more localized sort of connections there. We'll look at more of those plots in a bit, right? But now let's go into the question of which models of diffusion are actually most accurate. How do the network-only, identity-only, and full model compare? So I'll start with the null model, and I'm going to show you both of the measurements in the same slide here. So this one is looking at how well you were able to capture the pathway strengths. So here, the more the better, and this is the result for the null model. Then I'm going to show you what fraction of the simulations had an L that was larger than 0.13 in the broadly similar territory. And this is the null model, so about 9% of them in the null model had a broadly similar score. And then will show the very similar ones, larger than 0.4, and then we can see that the null model has effectively 0 pathways that were very similar, as we would expect. The null model doesn't perform very well. But next, we're going to ask, like, what happens when we start to bring in the identity and the network components? And what we see is that we do better, right? So we do better in terms of the pathways. We also do better in terms of the kind of least L measurement. If we compare between the two, what is better to use, network only, identity only, you get slightly different, like mixed results. So for the pathways, it seems like identity is a little bit better than network. But for the sort of final correlations, once the cascade has kind of fully ran, then the network seems to be a little bit better than identity. And here the question is, what happens when we actually combine the two? And sort of a reminder that, you know, a good guess could be that we don't get any further improvement in performance because the network only measure already captures all of that sort of identity stuff, right? Because we have homophily in networks already. But actually what we see is that it actually performs better kind of across the board. So combining the two does give you a boost in sort of capturing these types of dynamics. So the main takeaway for this, the first part is identity performance do better than the whole model. So they kind of individually capture something. But if you want to kind of model this in the best possible way, you really should include both the network structure as well as the identity of the agents. Next, so any questions about this so far? Cool. Yeah, go ahead, please.
Is there any way to untangle the role of people that have extraordinary number of connections? So I could imagine that someone takes a word that was introduced by someone else, right? And then broadcasts it, and now they have so many connections, and it kind of really drives things. And that person, so I'm thinking about someone like Elon Musk, right? That likes to be funny and it's copying other people and taking ownership of what they do. And the word could have started with some identity in the initial people, and then, you know, it's kind of loses it and gets adopted because of these other individuals. And we know that in the social networks, of course, there are some individuals that have many connections than others. Is there a way in which, you know, sort of having these hubs is actually making prediction harder? And that kind of, if it gets to one of them, then the dynamics become sort of harder to figure out what's going on.
That's a great question. I mean, we haven't done anything like that where we look at the effect of these hubs very much. But my guess is that it probably would change. I don't know if it would become harder or easier, right? Because depending on, they may have very...
If the identity is maintained, if the identity of the hub is maintained with regard to the original one, right. I think it would make it kind of, because there is also a lot of kind of identity related to you following one of these people or not. Exactly. But if it was sort of, you know, I mean, some of these people are not the brightest lights, and so it's kind of, sometimes they don't. You know.
No, that makes sense. But I mean, like, I think this discussion is interesting because, I mean, it's at a broader question that we had when we're modeling this, and that is, to what extent is it reasonable to assume that this identity of the word remains constant after the first initial adaptive, which is kind of what you're getting at, this can change. And in the kind of linguistic literature, we see that it can go either way. So like most of the time, a word has an initial kind of identity, signals an initial type of identity. And then even if people outside of that identity group continue using it, they still recognize as a word that had its origins in a particular, you know, in a particular kind of cluster identity group, right? So that tends to happen a lot. Now there are cases where it gets used so much that it kind of loses its original identity. So that can happen, and we're not modeling that. Like in our model, that stays constant. It would be, and the problem is sort of trying to figure out like when it will go one way versus the other, which may have to do with like who are they actually. Maybe it's about who are the celebrities who use the words.
Yeah, and I think this, because I mean, I was looking at the numbers and you see this very dramatic increase in performance, right? But the numbers are still, you know, 12% or something like that.
Yes.
And I was thinking, why. I mean, the model is capturing so many things that are important.
Right.
And so that's why I started having this idea. And maybe one possibility is if you could kind of keep track of the average identity of the people using the word, you probably could see if there are some transitions,
Right.
which of course, if there is a transition, it's kind of in the model, you are not including that part, right?
Yeah.
That someone that is very influential picks something up and kind of starts changing the identity. And so it would be very hard for you to account for it.
Of course, of course.
But I think it would be at least interesting to
Yes.
quantify the frequency, because it could explain about limits of predictability, of accuracy of your model,
Absolutely.
right? That it's not fair to ask you to predict something like that, because that was not in the construct.
Exactly.
Anyway, I don't.
I know that I agree 100%. The other thing I wanted to say is that I'm glad you brought up this issue of, you know, network plus identity does better, but it's still not great, right? The whole thing, you know, the numbers are very low. So like a couple of things I want to say about that. Yes, there are like definitely lots of ways in which you can improve the model. And what the other kind of thing to realize is we have all that we feed to the model is like the initial adopters, right? Of course, as well as like the network structure and the identity, right? So in some ways, our goal is not necessarily to maximize the total performance, but to make these comparisons. And yes, there are like definitely lots of different ways in which we could improve the model more generally, including that.
And I didn't mean to say that. I mean, I was not saying, oh, 12%. That's
no.
I'm actually, I mean, considering all the diversity of things, you have to be realistic about, and you are comparing with one realization of this thing in the real world, right? With a stochastic thing, it's like you shouldn't expect 100%.
Of course,
right? So it's I didn't mean it from that regard. I meant it in sort of I thought there could be some ways in which you could quantify the limits of how well you could do.
No, I know, and I know where you're coming from. I just wanted to sort of clarify that point. Absolutely, this idea of sort of tracking the identity of the word as it is diffusing is something we've thought about and something we potentially will try. Yeah, absolutely. Okay, so let me get into now why this is happening. Like, when is identity important? When is network important? What does it capture? What does each of them sort of capture, right? And this is, so when we look at some of these strong pathways for each of the models, we start to get a clue of what's happening. And so here are the path analysis, like not super easy to see, but here are the strongest pathways for the network-only model. And what you can see is that, again, like, there are a lot of connections between cities, right? Like lots of like intercity connections. Here is the strongest connections for identity-only model. And here you see sort of some intercity connections, like cross coasts and things like that, but a lot of kind of more localized types of structures here, where like more nearby counties are getting connected to each other. And when you combine the two into the full model, then you see just a sort of a blend of the two, where we have like the urban centers connected, as well as some of the more local connections. And so this sort of gives us a hint that maybe urban and rural areas are sort of using these two mechanisms differently. And that's exactly our hypothesis, right? So when we think about urban centers and look at prior literature of diffusion and adoption of kind of like cultural artifacts, we know that urban centers tend to be large, diverse, and they tend to be the first adopters of some of these things. And then subsequently, then these things get adopted in more rural areas, and they start to kind of signal a more kind of local identity. Now, when you think about the sort of what we know about diffusion and different types of diffusion, there is, on the one hand, the sort of Granovetter strength of weak ties type of argument, where things diffuse across people who are very different from each other and have weak connections connecting them. And then there's, on the other hand, there's the more kind of complex contagion type of argument that says that you actually require strong ties or repeated exposures from people who are very similar to you in order for you to adopt things, right? And so putting these things together, our hypotheses are going to be that this weak tie diffusion is going to control transmission across urban counties. And for that type of diffusion, the network is key because it requires these sort of very robust or this abundance of weak connections between urban counties. Whereas for the rural counties, they're going to rely a lot more on the sort of a strong tie diffusion that is going to sort of rely a lot more on identity. So having a high similarity of identity between the agents as well as a sort of consistent signaling of the word, right?
I have a question. So you say the weak tie diffusion control the urban counties and network is the key. Are you actually saying there's just no strong tie in the urban?
No, it's not that there are strong ties, it's that weak ties are more prevalent and they're more important for the transmission of the, between urban counties.
So it's because the weak tie are more abundant. No.
But it's because the weak ties are more abundant and because there is this sort of difference in the way that people in urban centers tend to adopt the cultural artifacts. That they actually want to sort of try out new things that are not as necessarily common currently. They're happy to kind of copy this thing that's happening in LA, even if we're actually very different from LA in our identity.
So can you distinguish that the abundance of weak tie dominant or because the people are just different in the urban area?
So it's a combination of the two.
Yeah.
Okay, and so next what I want to do is I want to see to what extent our data and our simulation results align with these hypotheses. And so I'm going to do that in 3 different ways. So first, I'm going to show you that the model performance is consistent with this idea. So what happens if I take just the urban to urban counties and see how well the model is performing only on those, right? And so here's what this shows. It shows that, well, when you only look at urban counties, the network only model actually does better than the identity only model, and it does better than the combined model, showing that the network is really what matters to capture the strengths between these types of pathways. For the rural to rural pathways, it's the opposite, right? It's the identity only model, the one that performs best, and the network is pretty much useless, right? And so we have this sort of consistency, right? So the network being key for transmission between urban centers, and identity being key in rural to rural pathways. If we look at the pathways that sort of connect the two, urban versus urban and rural, going in either direction, we see again that the full model does better. Okay, now from the distribution perspective, like how the data is distributed, in particular how the weak ties are distributed, this is perhaps not so surprising. So if you focus on the blue bars, this shows you the distribution of tie strength in the urban to urban pathways. And what you see is that basically they tend to have a higher density of weak ties, again, as you may expect. And for the red one, as rural to rural, they tend to have a higher density of strong ties, which again aligns with our hypothesis. If you look at how similar the pathways are, so again, looking at our 5 different dimensions of identity, we see that the rural to rural pathways, the red ones, tend to have more similar connections than the rural to rural. So that also aligns. And then finally, what we're going to do is we're going to compare the empirical pathways and how they change as a function of the simulated network only and identity only pathways. And so before I show you the results for that, let me kind of summarize what we would expect would happen, right? And so if we take only the rural to rural pathways, again, this is controlled by strong tie diffusion, where we have the importance is to have strong ties and high similarity. And we think about what will happen to the empirical pathways as a function of the identity pathway strength. So this would be the strength of the pathways when we use the identity only model. And then this is the network pathway strength, which would be the strength of the pathways in the network only model. And so as we kind of increase on the y-axis, we get more strong ties because this is the rural to rural pathways. And as we increase on the x-axis, we get higher identity similarity. And so what should happen to the empirical ones, right? According to our theory, it should say that the empirical ones should kind of increase as a function of both of these two. If we take the urban to urban pathways, again, this is driven by weak tie diffusion, then now as we increase in network pathway, then we are getting this higher abundance of weak ties, since that's what happens in urban to urban pathways. And on the x-axis, we get higher density or higher similarity. And so now the direction of the empirical ones should be different, right? It should be best when it's kind of in this area where you have, strong network pathways through weak ties and lower similarity, right? And so it should kind of go this way. And so that's our hypothesis. And furthermore, we also think that the effect of identity on the empirical pathway is going to be amplified by having a higher network strength. In other words, there's also some interaction effect. And so if we run a simple model where we say, put the dependent variable is the empirical pathways, and then we see what happens as a function of the network pathway, the identity pathway, and the interaction between the two, what we would expect is that for the rural to rural, we get a positive beta 1, beta 2, and beta 3, where beta 1 maybe is not as important as the identity one for the rural to rural. And then for this one, we would expect a higher or a positive beta 1, network matters, but identity actually hurts, and then the interaction hurts even more. And so that's our expectation. And when we check, that's exactly what we see, right? So here's the beta 1 for network effect. So it's beta 1, the coefficient for network. And we see that it's positive for all of them, largest for urban to urban. Then when we look at the beta 2, it's negative for urban to urban and positive for rural to rural. And then the beta 3 interaction kind of goes in the same direction. And so again, this is a third sort of way in which what we see in the data and the simulations matches what our kind of hypothesis is. And it helps us understand why it is that you benefit from having both of these incorporated, because one is important for rural transmission, the other one for urban transmission. So those are the main takeaways. The network better approximates pathways in urban to urban counties. Identity better approximates pathways in rural to rural counties. And then network and identity are required for a transmission between urban and rural areas. So I will conclude, I think, completely the talk. So we have methods. We develop an agent-based model to simulate the spread of these new words. We also create this database of lexical innovations by relying on this urban dictionary and a lot of filtering from many different ways, which actually took a long time. And then our main findings are that modeling these geographic patterns require that we pay attention both to identity and network homophily. And then network tends to really matter for urban to urban diffusion. Identity tends to really matter for rural to rural diffusion. Let's see, am I supposed to end at 150 or can I take a few more minutes?
A few more minutes.
Or maybe I'll do questions, and then if there's time, I'll say a little more. Yeah, go ahead.
Is there like a particular area that the initial adopters tend to congregate?
That's a great question. I don't know if we've looked at that. I don't know. Yeah. Good questions.
It's really nice to see the rural urban distinction. We might talk about rural, which is hard to study. Those people, and you mentioned that in your data is a self-reported location. To what extent do you expect that self-report to be accurate, as opposed to very much biased towards the rural side?
Yeah, that's the urban side, right?
To the urban side.
Yeah. No, that's a great question. So I'm not as concerned about accuracy because the way that we capture location is through the geolocation of the tweets themselves. And so if you're in a particular location, we'll get like the coordinates of where you're at. And so it's not that we're not using the sort of self-reported location in Dubai or something like that. So I'm not so worried about accuracy. I maybe are more concerned about representation. So that's something that does come up, and that is so we do a number of checks. For example, we look and see if somehow the frequency of interaction between people who are connected in urban versus rural counties kind of systematically varies, because that would kind of create those problems, but it doesn't, right? So people in urban centers have more connections, yes, But given that you have a connection, and the frequency of connection is not, it doesn't vary significantly between the two. So we do a number of checks to make sure that we don't have a kind of a representation problem, but I don't think we would have an accuracy problem. Yeah.
Great.
Questions?
Do you mind going back to the slides where you were comparing to the 4 conditions for like urban to urban or like urban to rural area? I want to make sure my question was valid.
Is this one or?
Yeah, like a few slides before this.
Don't even stop if you see it. Is this one?
Yeah. Probably one after this. Yes. I was just wondering, because in this case, the null condition performs better than network only.
Yeah.
How would you interpret that?
Yeah. That is a good point. So let me just go back here. Yeah, the null condition. Yeah, well, I haven't thought about that too much. I mean, we mostly paying attention to, I mean, like this one does better than all of them, and it improves, and then in particular it improves over these two. Why would the null one do better in this case? So we have the null one would capture things like population size of these locations. That stays in the null model, as well as where the popular people are. So I guess what it says is that if you're looking at transmission between urban to rural or vice versa, what really matters is size and then the connection of the people who are there. Much more so than if you're trying to capture rural to rural or urban to urban. I mean, that is like just reading the interpretation of these like at face value, like what it says. Like why that is, I don't know. Yeah, it's a good observation. Yeah.
When you say that you assign a location to a user, so you can imagine someone that travels around, so or a lot because of work, or someone that doesn't travel very much.
Yeah.
And so, do you kind of assign all the tweets to sort of the stable location?
Yeah, right. So people will have different locations, and there are kind of ways that we can define a certain radius of where they're at, and then take into account how much they tweet in different places, and we take the most kind of common locations. And typically those distributions are pretty skewed, where there's like a clear one. And yes, people sometimes like leave, but they tend to stay in one place for the most part. Yeah. Yeah, because we get a different one location per tweet, and not
right. And I imagine someone that travels a lot around and
could
that would be.
Piggybacking on one of the earlier discussions, the linguistic innovation seems to be very rare. So you have 76 instances here, and I really appreciated how carefully you chose those. But then how does that reflect, or how does that impact the way you can interpret these accuracies? So
yeah, we have a small n. So I guess what I would say is, I mean, typically we actually have the opposite problem when we use social media data, right? That like the significant value, like the p-values and stuff, are like pretty uninformative, because everything is significant and we're just picking up like tiny effects. So I guess what I would say is we don't have that problem here as much, since we only have 76 of these. So we don't get like the significance, say, for free, right? But certainly, yeah, it's a small n, and so it'd be great to have more. So kind of along those lines, I mean, new words are, it's an interesting phenomenon, and it's fun to work on it. The way we're thinking about the model is more generally, can it capture more kind of general diffusion of cultural artifacts? And so we're kind of in the process of testing out the model using other types of things, both within social media, say hashtags or topics of interest, things like that, but also outside of social media in terms of like music tastes and other things like that. And so the model is meant to be more general than just just new words. Just new words like was a kind of a fun one to try to start.
Yeah.
Yeah.
I would make a comment. In biology, usually if you have 3 biological replicates, you are happy. So 76 in that would be kind of a factor of 20. So it's small, but I mean, what is small and large depends a lot. So
That's true.
it's a pretty significant number.
Yes.
Have you, like, this kind of reminds me a little of like cultural evolution, especially when people like measured cultural evolution through like linguistic related changes. Have you thought about how this maybe like relates to that?
Really? So can you say more? So how?
Yeah, like, you know, I guess it's slightly different because this is like linguistic innovation. So rather than like evolution, but maybe if you know, I've seen like work that looks at how maybe the usage or meaning of words changes through time, like region-based, like
Yes.
similar network models. So,
Oh, I see. So you're saying like modeling, not like innovation of new words, but like shifts in meaning.
yeah.
So certainly, yeah, that's interesting. So, I mean, there's work that tries to measure when that happens using language models and embeddings to try to kind of understand when a particular word seems to have changed meaning by looking at what other words they relate to. So I think the identification of these happening is something that people have worked on. Yeah, it could be. Again, it's possible to basically apply the same pipeline to see whether, you know, identity and networks actually can basically either predict those changes, or given that there was a change, try to say something about where this word would now diffuse now that it has a different meaning. So yeah, that could be fun to do. Yeah. Sorry, I didn't quite understand it the first time.
You mentioned that there was this interesting component of the data that for now did not touch that.
Oh, yes.
It seems like for identity that might be a very big driver. So can you speculate then, or just walk us through the process of deciding not to include that for now?
Yeah, okay, so there are a few things. So the first is, while we could do it for some, we couldn't do it for all of them. So we're gonna have that limitation anyways. So for example, political affiliation, there's some work that tries to do it. SES, it's much harder. I guess languages spoken, probably you could get from the data itself. So one limitation is, you know, how do you do it consistently for all of the dimensions, right? And then the other consideration is, we know that many of these algorithms work differentially for different populations, and so we could probably get, you know, do it really well for certain like types of political affiliations, but much worse for others, and so that would introduce certain biases. And then the other one is that a lot of the work that tries to do this actually relies on the network structure itself. And so we were concerned about basically baking in the effect of the network by using the network to predict these properties, right? And it was a similar issue for location, right? So we could have a lot more nodes, a lot more than 4 million agents in the model, if we were willing to use inferred location as opposed to the exact location. And there are algorithms that do it really well. In fact, one of the co-authors, David Jurgens, he developed one that is very popular. But again, it relies heavily on the network. And so by applying it, we're baking in some of the network effect by using it to make this break. So that was kind of another consideration. So yeah, no, it was tempting, but we ended up deciding not to do it.
Okay, wonderful. We are at the hour. I'm afraid we have to stop now. Thank you again for being here. Don't forget to grab your lunches and see you next week.
No, see you next fall.
We're kicking off in the fall with, thank you, Daniel, thank you, Agnes, for moderating. And we're kicking off the fall with Dean Julio Latino. Will talk with us on September 28th about his new book, The Nexus. So yes, please grab a lunch and we will see you in the fall.